gives me tremendous pleasure to introduce two colleagues, friends that we've only known each other for a couple of decades.
Half, maybe.
Andy Shapiro and Jacob Racusin. And there's so much stuff happening talking about carbon and embodied carbon. It would be nice to talk to people or listen to people who actually know stuff. So please tell us stuff.
Thank you. Thank you, everybody. You know, I've been blessed with many mentors over the years, and many of whom are in this room, who I greatly appreciate. I call myself a high-performance building design consultant. And people go like, what is that? Well, I look at building enclosure. I start with, what is it people want to accomplish? What do they want this giant thing of stuff that they're creating to express about their connection to the planet and their connection to the people inside the building? Starting there, then looking at the enclosure, the mechanicals, the moisture, the ventilation, the materials choices, operational, and then I go, and in my better projects like the case study today, I'm not only the energy consultant, but also I did the enclosure commissioning, and we've got an E-gauge which monitors all the circuits, all the major circuits in the building, and I'm tracking this building for a year. How did we do? You know, these buildings we have aspirations for. If we don't do that, we don't know. About a decade or so ago, I kind of put it out there. I was interested in teaching some, you know, and trying to give some of this back that's been given to me so often. And this young guy comes knocking on the door. Like me, when I had a mentor, when I started out at age 26, I had a year at liberal arts college, and he started me with pencil and paper doing heat transfer and energy modeling. So Jacob shows up at my door, and we've had a wonderful relationship ever since. This is maybe the first half of that decade I was mentoring him, and the latter half we've been colleagues. And I've been learning from him on the things you're gonna learn about from him today.
It has been a deep honor and privilege to be able to receive mentorship for Andy and have that be my entryway into this community. So gratitude to Andy, Joe, and Betsy for creating the space and leadership within this community and having us on stage. My entry into this whole world was actually as an owner-builder, as a young 20-year-old needing to build a home for my family, and that emerged through practice in northern Vermont, working with natural materials into the realm of building science to be able to vet out the viability of working with some of these materials and techniques. The evolution of the building science focus around working with these materials led to an expansion of the boundaries of looking what the larger climate impacts of these materials are, which is what's brought this issue of embodied carbon to the fore, looking at this from a material basis. But to be able to do all of that without any higher education was made available to me through the structure of mentorship and the knowledge sharing and learning that's so present in this community. Christine did an amazing job of highlighting the value of that yesterday, and just want to re-amplify how important mentorship is for the transfer of knowledge to keep these ideas and our practices evolving. So I'm a product of that, so it's an honor to be on the stage.
So you got kind of, well, we've been talking about what to call this embodied carbon. It isn't the carbon embodied in the building, it's the carbon dioxide emitted in the manufacture and use in the building of materials. And that's such a handful that's hard to say. We just say embodied carbon, even though that isn't really what it is. So if you got embodied carbon 101 from John on the first day, you're gonna get 102 today. This will all be on the quiz, and we're gonna do it through a case study.
All right, so just to give you a little more specifics about what we're gonna be getting into today, it's going to start to defining some general terms and concepts, sort of set the table for us all around understanding operational and embodied carbon, to make sure our terminology is correct. Andy's going to take us through the case study, which will be the bulk of it. And then we're going to look at, from a slightly broader lens, how we think about analysis and conducted analysis and looking at both operational and embodied emissions, and look at what's coming up and some of the actual practical applications of this and the sort of the direction of this work within our community in the very near term. So let's start with language. Annie did a great job of just identifying embodied carbon as really shorthand for embodied carbon dioxide equivalents, emissions explicitly, and the E behind next to the 2 there, that E is for equivalent. So when we see CO2e, or we talk about embodied carbon sort of colloquially, we're talking about not just carbon dioxide, but all the greenhouse gases that are emitted up into the atmosphere. We look at what their relative impact is compared to a molecule of carbon dioxide, and it is assigned that value. And then all of those values are combined together for a single metric of CO2e. So for example, methane is roughly 30 times the impact of carbon dioxide over a 100-year period of time. So it has a global warming potential of 30. So when the CO2e, that's the unit that we would be using. So it's not just carbon dioxide, it's really all greenhouse gases. And if you see GHG out in the world, it's an equivalent metric. So I want to really just define the life stages here. What's a really big conceptual leap from those of us who have been in the energy space for a long time is our temporal and our spatial boundaries are greatly expanded. We're not just looking at the building during time of use, we're looking at everything that happened upstream and downstream. So embodied carbon is the terminology it's used for the entire life cycle. Life cycle assessment is really looking at this whole life cycle, and it starts with raw material supply and transport. Here, we'll do that. That product stage, John talked about the A1 to A3. This is the extraction of raw materials out of the ground, their transportation to manufacturing facilities, and then the manufacturing process itself. That's also called cradle to gate being the manufacturer's gate. It's also called the product stage. And so this is or material emissions. Those are all the same words talking about the emissions that were released to create a product. When we talk about upfront carbon, which was mentioned during Dr. Straub's talk there as a perhaps more clear language, that is more clear language for all of the emissions that were released prior to day 1 of occupancy. So now it's looking at all the products, plus the transportation of those products to a building site, plus the emissions for the construction of that building. Obviously, it's going to be very different if it's a building in a cold climate that's under construction for a year and needs to be tented and heated than for a faster building that doesn't need temporary heating, but those are some of the emissions that would show up during that construction phase. All that together is the upfront carbon. Then we get into the actual use and maintenance stage of the building's lifespan. Ideally, a structural material won't need any additional inputs and there's no emissions associated, but high turnover materials like additional coats of paint, for example, or equipment that needs to get replaced out, there may be some repair and replacement and maintenance emissions that show up there. Operational energy and water also obviously occur during the use of the building. When we talk about life cycle assessment or embodied carbon values, the emissions from energy are separated out. So we look at those as 2 different metrics. So when we talk about embodied and operational, yes, they happen at the same time and can even happen in the same place, but the operational emissions are declared and reported discretely from the rest of the embodied carbon emissions. Just to be, that's terminology, and that'll be the framing for when we're presenting our data. You'll see those 2 buckets. Then there's also the end of life stage, deconstruction and demolition and waste management and all the emissions that come from recycling. All of that shows up in these end of life stages. When you're looking at all of this together, it's the whole life cycle. The language embodied carbon can be used to describe any parts of those, and that's where this gets really confusing and why we're taking a minute to really try to parse this out. But for the sake of expediency, so we're not using a ton of different terminology, we're going to be saying the words embodied carbon. It's going to be referring to all of those greenhouse gas emissions, and as we'll talk about in a second, most of that analysis is really from the product stage, with then some extrapolation from that in later phases. So the math around this is way simpler than energy modeling. We're looking at the quantity of material and then the emission factor for that material. So for any given kilo or pound of steel, there's a certain amount of emissions released, and you just do the math, and that gives you the product emissions. So you need takeoffs and be able to quantify your materials, and then you need a data set that tells you what the emission factors are for those different products and those different materials. So the data data can come from a couple different sources. There's a whole other realm of conversation around that. The data that we're using within our study and that we use for most commonly for looking at product emissions are environmental product declarations. Dr. Straub talked about this a bit as well on Monday. You can think of this as an environmental impact nutritional label for a product, and it gives 7 different impact categories, including ozone depletion and acidification of water. The metric that we're looking at is the global warming potential, which is not to say that these other things don't directly impact atmospheric carbon dioxide balance. The one thing that we're tracking is the direct emissions from a product into the atmosphere. And it's coming from these EPDs that are third-party certified following international standards that are released by the manufacturers themselves or their trade associations. So we have a high level of confidence in not the precision, but the sort of overall accuracy of this data as a sort of a viable data source. In addition to my work in New Frameworks, design build firm in Vermont, I also work behind the BEAM tool, which is a material carbon emission calculator with Builders for Climate Action based out of Canada. So we've developed this tool to make it easy and feasible to compare across these different products. EPDs can be really confusing. They can be hard to really understand what data you're getting out of them. Are these things comparable? The units are all different. They're not easy for an entry-level person to sort of dive into and start getting numbers out of and make sense of it. So we create tools to help process that information and normalize the units and the values and make these comparisons possible. So the BEAM tool we developed for this use and is explicitly looking at the product phase, that A1 to A3. And we will talk about the additional layers of the life cycle that we bring into our analysis.
And you can Google BEAM tool and go find this and use it. I actually could do it. It's pretty easy.
Please do. So A1 to A3, again, is that product stage. So it's the emissions A1, the emissions released from extracting a raw material, say out of the ground or from a forest. A2 is transporting those raw materials to a site of manufacturing. And A3 are the emissions released from the manufacturing process itself. And you add all those together, and those are the emissions for the product. And what gets a little confusing is scale jumping between a product and a building, which is made of a bunch of products and have a bunch of other processes in it. And that's where a lot of this confusion lies. We could spend an entire day just trying to break this apart. We do not have that much time, so I'm just giving you the Cliff's notes here, and we can keep drilling into those definitions as we need. So just super high level framing around the relationship between operational and embodied emissions. Because again, we're looking at those as separate metrics. There is some overlap, but there's also some distinctions in time and space and when those emissions are released. So part of what we collectively as an industry need to learn is how to combine those metrics together and make good decisions and conduct good analysis. So this is a hyper simplified graph of what emissions look like on the operational side. Nothing is a straight line, but this just for simplifying concepts. There's emissions that are released every year through the use of energy in a building. In this case, 3.5 tons a year for a code minimum 2-story home in Toronto, using a blend of natural gas and electricity for power. And then over a 30-year period of time, you assume there's no changes in the grid and assume the energy use is the same. Those are the simplifying assumptions. You add those annual emissions year upon year upon year upon year. And what everyone in this room has, I shouldn't generalize for everybody, but what this community has done a fabulous job of is really understanding how to reduce energy, and by association, how to reduce some of the emissions associated with that energy. That's what John was talking about on Monday. When we reduce energy consumption and use lower emission forms of energy, renewable energy, as opposed to, say, number 2 fuel oil, then that line gets lower, right? It's a lower amount of emissions that are released every year to power the building, and so as we add them up year upon year, it's a lower number. The thing is that we don't start at 0 on day 1 of operation. The clock actually starts when these raw materials are extracted out of the ground to create the building in the first place. And so if we want to encapsulate that part of the boundary of the building, we can't start at 0. We're actually, year 0, this is the beginning of operation. There's a whole bunch of emissions that were released prior to the operation of the building. And those are the embodied emissions, or the upfront emissions, that we're looking to capture and bring into our analysis. So that line of the operational emission sort of step change, it happens somewhere. This is what we need to figure out. What are the upfront emissions that mark the sort of starting point of the operational life of that building? So those are the 2 numbers we're looking at. And really the idea is that if we're trying to reduce the emissions of our buildings and build low carbon buildings, we need to do both. We can't just look at energy, as John did a great job of explaining, you can't just look at energy. You have to look at the emissions of that energy and the differences between emissions of, say, solar-powered electricity versus, again, number 2, fuel oil used to heat a building. And then we also have to look at those upfront emissions to get the full picture of what is the climate impact of our buildings. And for trying to get to low-carbon buildings, that's how wide our arms need to be to hold the scope of where the emissions are coming from our buildings. Turn over to Andy for the case study.
All right, we're going to take a look at this particular building, look at it, operational and CO2 modeling there, the embodied energy material. I looked at a couple of options on the operational energy side. If this building were just built to code, and this was the 4-year-old Vermont Energy Code, which is actually pretty good, versus the high-performance building that we actually built. And for the embodied, I look at kind of 3 options: the code building, the low operational energy building if we didn't care about materials choices, and then the one we actually did, where we did try and do a lot of caring about that. And then what got me really interested was what happens over time. I mean, what's going on in the atmosphere as a result of this? And that's going to be the fun part we'll get to. And of course, lessons learned always we always stub our toes somewhere, right? And I still have most of my toes. So this is at a beautiful little private high school in southern Vermont in Putney, and they wanted to build some new dorms. McClay Architects did these. They're gorgeous buildings. Bill McClay and I have been working together for 30 years or so. And with Bill, I've done some of the best projects I've ever done, been with them. The 2 buildings are nearly identical. Each one has 11 dorm rooms that are doubles and 2 3-bedroom apartments. That's sort of their school model. The faculty live with the students closely for keep an eye on them, I suppose. So you can see the apartments in red and the dorm rooms in blue, 2 stories, plus a basement, fully conditioned basement. And single-use bathrooms, which we'll come to a little bit. Gorgeous building on the inside, just a couple of beauty shots. It's a lovely space. Nice wood beams there, nice local wood used for all of the trim and so on. John Unger Murphy Celltech did just a fantastic job on insulation and air sealing and problem solving, which we'll get to here. It's double stud, 12-inch thick cellulose wall, R60 in the attic, 4 inches of EPS under the slab, and at the edge there's some polyiso in there, and glavel underneath, which I think I have a picture of here somewhere. There they are working on the spring and insulation. Of course, concrete is a big deal in embodied energy. Even I knew that. So we had this great specification, and of course, guess which one was submitted, and guess what percentage was finally submitted on? The lowest possible. Again, my job, I've learned over the years, I lead the horse to water. I can try and make him drink, but that's about it. So we did achieve something there. Here you can see the glavel going in. So glavel is like man-made pumice. Recycled glass is heated up in this special furnace kind of deal, mixed with some glycerin, high temperature, and it then is extruded onto this long conveyor belt, and it looks like lava, like man-made lava, 4 inches thick, and as it goes along, it's so hot it's cracking, and by the time it gets to the end of this conveyor belt and dumps out in the yard, it's broken up into pieces. And you throw it in a foot of this stuff, and it's as good insulation as, 4 inches of EPS or so. The square there, the compaction is different. You can keep compacting this stuff beyond what you should because it's pumice. You can crush it. So there's some finesse in there, but they did it, and it was not the first time for these guys on doing that. So here you can see it's a big 40-foot wide truss there, and our air barrier, the primary air barrier is zip sheathing, taped to the foundation. The concrete continues the air barrier around the bottom, and it goes up the other side and goes across the attic floor here. Our spec was 0.05 CFM50 per square foot of shell, 6 sides. As I told the guy, the site super, I said, my job is that when you get to the final test, you're not going to be worried. I work with you. I help you figure out these details along the way. I do progress testing. We show where there's issues. Nonetheless, he was nervous. I said, I can be the bad cop. That's not my job. My job is to make sure you get it. And they did. They hit 0.035. That super tight bill is very pleasing. And you can see some of the detail there on the left. John Unger Murphy did fluid applied. It's a Tremco Exo Air vapor permeable liquid applied air barrier on the outside. So now energy and operational energy and embodied energy modeling. I'm going to walk you just really quickly through the comparison of these. You can look at the slides if you want to dig into what was done here. So for example, Windows code, our low E argon dual pane, we did tri-pane, doors more or less the same. I showed you what we spec'd there for concrete. The walls, basically we looked at steel stud walls with exterior insulation and cavity insulation for the cases, the 2 cases where we didn't care about embodied emissions. And wood studs, 12-inch, you saw that. Basically, you saw all of this before. Cladding, we looked at fiber cement siding, which is kind of pretty typical for these buildings. Instead, we used locally milled cedar. We did use oil base, which was higher because we wanted to preserve that cedar with the semi-said transparent stain. All of them had metal roof, steel studs versus wood studs, typical gypsum board. We found this EcoSmart gypsum USG. It's half the weight, half the embodied carbon. What's not to like? Didn't cost more. And this was, a change on the fly during submittal process. I spent a lot of time going through submittals. That's part of my gig. Locally sourced trim wood. And, the code called for 0.3 CFM50 per square foot of shell. So we did 6 times better than that, 7 times better. Maybe it's 8. So mechanicals, commissioning not required. Of course, we did that both on mechanicals, and I did it on the enclosure. Ventilation, we did the same everywhere. It seemed like a place you could cheat the model, so I didn't want to do. Although the code does require it in Vermont. Hot water, could have been a boiler, but no, we did. I'll show you the hot water we did later. Heat would have been a boiler. Split system AC. We have city multi heat pumps here. Use the same set points and lighting. Building enclosure, we paid attention to details, like slab edge down here and capillary break here to minimize water wicking up through the wall, even though we've done a great job of excluding it. At the top of the wall, here's that detail where the primary air barrier goes from the outside, that exo air out here. There's a plywood plate that goes across the top of the 12-inch wall. And notice how it sticks in a couple inches. Because there's Intello, I've learned by monitoring moisture content in my own home, where I have a 12-inch double stud wall with no vapor barrier in there. Moisture content and exterior sheathing got up in the 30% on the north side of the building. My building is built with boards, not plywood, so we feel like it's not going to fall down. But that put the fear of God into me. We put Intello on these walls. And so we needed to land the Intello from the ceiling to the walls, and so we gave them this little lip there to land it on. So I'm on site one day, and the thing's all framed, the trusses are up there. Where's the lip? The site super says, what lip? I said, the lip, I describe it. It's not in the drawings. I said, let's go look at the drawings. Well, it's in the drawings. Therein lied a bunch of fussing. John Unger Murphy at Murphy Cell Tech, he got up in the attic. I'm down there with my pressurized fog device on that joint in the Intello. He's watching the smoke, the fog come up through the attic. No matter how they taped it, ended up spray foaming that joint from the attic. The CM was good about it. They always took the attitude, all right, how do we fix this? It wasn't like who shot who. I think the client ended up paying for more of it than he should have, but that's a whole nother story. This building has 22 corners on the first floor. It looks great. It is a pain in the neck to get a good enclosure with 22 corners. And then that picture in the upper left there, cathedral ceiling joining a little tiny attic, too small to get into and do it. The GC, the CM, super, me, the installator, the framing contractor, we had many head-scratching situations because this wasn't completely detailed. So it was a bunch of time wasted because this building was so complicated. It does look great, I give it that. So hot water, I really went after hot water. This is a drain water heat recovery device. How many people have an idea what this is? Okay, enough that I'm gonna say. It's in the drain, you put in a piece of this thing, it's a copper section of drain pipe. Wrapped around it is, in this it looks like one, but in the commercial one it's 3 parallel tubes wrapped around it. And it turns out that water falling down a drain doesn't go down like a ball down the middle. There's surface tension. The patent is called a falling film heat exchanger because it forms a film on the side of the pipe as it goes down. And so you get this great heat transfer. You run the cold water when you're taking a shower, you're running cold water into the water heater at the same time it's going down the drain at what, 95 degrees, 100 maybe? Probably 95, 90. It's going down there and you can capture half of that water, half of the heat in that water from the shower with these things. Maybe $1,000 for this thing. Where else can you get half your hot water for that kind of, well, half your shower water for that kind of price? So these are gangbusters cost effective, but you have to gang your bathrooms. So we have 3 showers on each of 2 floors, one above the other. All of them drain into this one heat exchanger. This one, Power Pipe, is one of the brand names. Drain water heat recovery is the generic. And then I'm enough old school that I still do solar hot water in places where it makes sense. Got to be a big load, got to be used in the summer. And these dorms are used in the summer because they're air conditioned. And they realize that when they're running summer programs these days, this is going to be needed. It's what's called a closed loop drain back solar hot water system. There was a guy named Ev Barber who took care of old orphan solar hot water systems from the 70s, and he fixed so many of them, he knew what worked. And this is what works. I have one in my home. It's 15 years old, no maintenance. The glycol pH is still perfect. Talk over beer if you want to know more. Embodied energy in this thing is going to be there for 50 years. It's not like a heat pump water heater with refrigerants that are going to go somewhere and going to be replaced every 15 years. Here's the schematic of the system. You can see the collectors on the roof, 6 4x8s, 219-gallon solar storage tanks feeding 2 heat pump water heaters. We tried to, I'm going to say tried, here's one toe that got stubbed, to eliminate the recirc system because those systems can use as much energy as the actual usage of the water. So ganging those bathrooms helped with that too, because we could put these tiny little risers up to the labs so you didn't have to wait for hot water. Never mind that the code says half GPM on the aerators, so it still took forever. And I ended up myself, because they wouldn't do it, the plumbing contractor wouldn't do this, I swapped out the aerators for 2.2 GPM aerators so that you get hot water instantly. And I don't think we're using any more hot water. Now I'm measuring hot water, so I'll be able to see if this is really true. So with the monitoring now, I'm monitoring the water usage going into the system, and I'm monitoring all the electricity used in this system, and we'll get some overall COP for this. My early data is pretty funky. It's not showing great stuff, and I think I've got some data problems, but stay tuned. So here's my operational energy model. I modeled it at about 15 kBTUs per square foot per year. This is the typical energy usage index, or EUI, that allows you to compare one building to another pretty easily, versus the code building. You can see there's a pretty nice reduction there. I think we're going to be closer to 20, probably 20, 21 kBTUs per square foot. Still a decent building, still pretty good. And why that is, stay tuned till we get this modeling, or the monitoring. Now here's the carbon dioxide equivalent emissions. So this is the big story. This is really why we do this. Electricity is expensive in Vermont. There's no natural gas in this area, so we do save over oil. With propane, not so much savings, but still good savings. This is why we do it. So if you look at those two graphs together, you can see on the left, the operational energy, I don't know, we're probably 40% of the code building, but the emissions, operational emissions, are really low. Good so far? So here's me, monkey in the typewriters on the beam tool. And so here are the different elements of the net zero ready, we'll call it, building as built. Here's the net zero ready materials if we didn't care about the materials. And here's the code building. Yes, this building would use more if you didn't, more embodied energy, because you got more stuff in it. You got more insulation, you got thicker walls, and so on. And you can use this to see, well, where's the big deal? What's this big red thing? Interior walls, remember the baseline building had steel studs, wood studs. I'll come back to what this little bump is up here. Notice our insulation is below 0. So we count cellulose as actually carbon storing, and Jacob's going to talk about that. When do you count wood as carbon storing? When don't you? Wood-based products, bio-based products, not universally storing, but something that's a recycled product that might have gone in the landfill otherwise, I think we can count that as carbon storing. So we get a little bump, negative bump there. Now, in this one, I've taken all of that A1 to A3, this will be on the test. This is cradle to gate, resource extraction to when it left the factory. That's now all compressed. The entire bar chart from the previous one, that whole bar on the left is now that blue bar, the blue part of the bar at the bottom. And we made estimates about the energy it would take for construction, what those emissions would be, the emissions from maintenance and use on top of that, the end of life on top of that, MEP. So MEP, all of that stuff has been hard to find. And Jake has been doing a big research project on that lately. That's coming. And then refrigerant leakage. So refrigerant leakage is not a small number. And I use the 20-year equivalent because I don't think we've got 50 years to solve this problem. Right, so I use the closer one. Like on methane, I use 86, not 20. I use the 20-year one.
And so just to explain that, when we're trying to value the global warming potential of a greenhouse gas, the sort of international convention is to look at what is that impact over a 100-year period of time. But if you're trying to figure out what the impact is within near-term climate goals, like 20 years, those numbers are much higher because the decay rate of the chemical in the atmosphere. So it's really high in the near term. And then in the case of methane, as you just mentioned, it decays over that period of 100 years. So like maybe, 28, 100 years from now, it's 86, 20 years from now.
Area under the curve might be, whatever. All right, so now what is all this doing? Okay, we've been doing all this work. We've been trying to make these great buildings. We've been trying to save operational. So what happens? Well, all right, stick with me here. So the grid, this is an all electric building. Grid emissions are expected to change over time. I would have said a year ago, we expect them to decrease over time. Given the current situation, maybe not. Maybe that's a straight line there, starting at this is ISO New England numbers, our regional grid. It's, give or take a pound of carbon dioxide equivalent emissions per kilowatt hour, give or take. Cambium model was developed by folks at NREL to look at various scenarios for what's it look like. And you can look this up for your regional electric grid, you can look it up by state. I think the regional one's a little better for a bunch of reasons, so I use that one. And then you can pick scenarios, business as usual. It was interesting, none of their scenarios had the tax credits going away. But I picked an optimistic one here, 90% better by 2050, give or take. So our 95% decarbonization by 2050 scenario. I mean, 2050 is still 25 years out, but still, this is pretty optimistic. So I wanted to look at the optimistic case here. You with me so far? So this is, you know, each year the grid gets a little cleaner. Then I thought, well, what happens to this CO2 in the atmosphere? I mean, let's say we put it all in one pulse, simplifying assumption. 1 year, it all goes up as a pulse. Turns out it decays at about 1.5% a year. So you get this nice long tail of the curve. The far right number on the x-axis is 100 years. So this is a long, slow decay. I thought, oh crap, this stuff is going to be around for a while. This is not talking about where it goes and is that good or bad or indifferent, but just what it's doing in atmosphere, because that's what's doing the forcing of climate change. And you can look at this under the curve. So this is what it's that same curve, only run out 50 years here. So it doesn't quite taper off as far. That's what's in the atmosphere from the first year of operational energy of this really good building. Crap, it's 35,000, 40,000 pounds in the first year and then decaying from there. So then let's add on each year on top of this. And recognizing it, each year we're going to make the add a little smaller because of that previous, you know, because we're making the assumption that the grid's getting cleaner every year. But then each year's pulse has a tail, right? So what does that look like? So here now we've got 25 years of operation. You've got 25 bands there, looking at it over 50 years. This is my really, you know, great building. I'm so proud of this building. Crap, we are up at, we are up at near 400,000 pounds in the atmosphere from one of these pair of pretty good buildings. I'm dismayed. Okay, I got to follow this out. Let's keep looking. All right, now let's put in the embodied energy under that. So that blue thing at the bottom is the A1 to A3. That'll be on the test what that is. It's cradle to gate. So again, this isn't all the emissions associated. Remember, there's the whole life cycle bit going on. Let's just add that one in. All right, now let's add in all the rest of those life cycle pieces. Holy crap. And then I also added in here, see at the bottom, refrigerant leakage. So this is an R410A system, global warming potential, what, 1,800, give or take, times carbon dioxide?
2,100.
2,100 times carbon dioxide. This is serious stuff. It does have a faster decay rate, but it's not, their decay rate is not immediate. It's still hanging around. And there's a bunch of studies showing 5% leakage rate per year is kind of an average. Now, of course, it typically doesn't happen that way. You may have no leak and then a bunch in year, whatever, 17, 5, whenever it happens to leak. So, okay, now we're up to 900,000 peak, almost 1 million pounds in the atmosphere from this one really good building. It's like, okay, I'm getting really depressed here. So I thought, all right, now let's look at this. Okay, that's just circling that 900,000 number. That's the same thing you just looked at. For all the stages of the embodied, from the beginning to the end of life of the building, plus refrigerant leakage, plus operational emissions. Are we still friends? Yeah?
The number for refrigerant leakage, GWP 20 or 100?
20, yeah. I think.
The question is whether this was GWP 20 or GWP 100 for the refrigerant. Again, what's the 20-year out or 100-year out value of that emission factor?
I use the near-term stuff. I wish we had 100 years to fix this problem. I don't think we got 20. Chris? Those are each year of operational energy emissions from the electricity used by the building.
For 25 years.
Yeah, 25 years of operation over 50 years. That's why you see that little inflection right here, that's when I stopped adding. But even so, you can see it would have, the maximum had been reached at something like year 20.
Grid scenario.
Optimistic grid scenario. Yeah, it could be double this. Well, double, the operational could be double, which wouldn't double this because of all this other stuff going on. I can't hear you, sorry. Where's our,
The question was, is the GWP 100 for the A1 to A3? The answer is yes, it is.
no, it's not.
Oh yeah, the EPDs are GWP 100.
Oh, okay, so okay, yep. Yep.
Actually, we should look at the refrigerant. I believe for this study, we used the 100 values for the refrigerant for consistency, but we need to just double check that.
Yeah. All right. Still friends, even though there might be some mixed metaphor going on here. Okay. All right, so I thought, oh, well, let's just look at this for the code building. This one peaks at 4 million. All right, I don't feel so bad anymore. We've cut this down by a factor of 4 for all this effort over 7 years between design and occupancy of this building. So again, energy use, you can see I kind of highlighted that here. So now for the code building, notice how the energy use is dominant. Doesn't mean you don't care about this other stuff. You know, that other stuff would all be big. Just, you know, you remember that the code building had a big embodied emission also. But just, you know, percentages make a difference, but that's not the whole story. You're really looking at the quantity of emissions. That's what we care about. So this thing is peaking at 4 million. So what did we learn? I still have all my toes. Some of them still hurt a little bit. The owner said, give us a great building. Do what you do. Give us a great building. It's fabulous. CM, we'd run into a problem. It wasn't like who shot who. It was like, let's fix it. Early engagement is important. Lots of corners and roofs make it really difficult. Cement substitutes are hard to actually get. They've got, you know, oh, this sub only works with this ready-mix supplier, and this ready-mix supplier only gets this one particular kind, and sometimes they get it and sometimes they don't. And they've got to have it. They don't store it on site. They don't have a special silo for this stuff. They got to get it delivered when it's needed. And so there's a bunch of coordination and a bunch of working with everybody. It's a people issue. Periodic testing and enclosure, absolutely critical. Show up. Okay, so I show up. Part of my gig as building enclosure commissioning is we have a pre-construction meeting. Okay, we have our pre-construction meeting. Subs are all there. We go through page by page of the building enclosure details. We look at each one. Good, questions, on to the next one. Well, this was 6 months before the framing contractor starts. I should have had a pre-construction meeting with each sub their first day on the project. Did my budget include that? No. All right, that's the big stub on the toe. Moisture management during construction. This is a smart builder, yet when they mudded the drywall in the building and the attic was not yet insulated, they didn't open the windows. They were afraid their heater wasn't big enough, I think. Well, somebody's up in the attic the next day. You have puddles, there's water covering the floor of the attic on top of the drywall. Sorry, on top of the Intello. The Intello that's drywall and then Intello, and then you're in the attic. And the Intello did a great job. It passed the vapor, and then it condenses, and of course it doesn't pass the water. So, job meeting. Cut out the Intello. I'll show you how we put this Intello in a minute. It was a beautiful installation. We had to cut it all out and dry this frickin' building out. And we had to dry it out in a hurry, as everybody in the mold business will tell you, and we did. And we couldn't replace the Intello at that point, so there's 2 inches of spray foam on that building. First building, the second building, they learned. Yeah.
Yeah.
Yeah, it shows up.
Well, just the blowing agent, but the actual product is significantly higher.
It shows up as a little dotted thing on that bar chart I showed you of all the different ones. I said there was a little bit on top that we had to add. That's what it was. Attention to detail and problem solving, great. Can do air sealing and insulation sub, great. Building enclosure and MEP commissioning, all good. And then we put in an E-gauge. So an E-gauge is this great monitoring system. It's got about 30 channels. We have 2 of them in there, monitoring about 40 channels of all the major systems, subsystems in the building. If you have a building with an energy goal and you don't do this and you don't meet your number, you go in your building and you scratch your head. And you say, well, it might be this, it might be that. We have this E-gauge. So I'm looking at the E-gauge. The ERV is not a good enough ERV. It requires post-heating in cold weather. Whether it did or didn't, that was an argument I had with the mechanical engineer. He has to sign off. He wanted it. Okay, fine. We can just turn it off. It was set to 65. How did I know? I looked at the E-gauge, and it was like going through the roof, this post-heating electric element, and so I could see that. And I could see that one of the heat pump water heaters was set on resistance heat. And I could see that the solar hot water pump was using 300 watts, 2.5 amps, when the controller was only rated for an amp. All of this stuff. So these things are gold. Maybe it's $15,000 to get this thing installed, and probably that again, if you had to pay anybody to look after it. And I don't charge nearly that amount. I call it unfunded research. And I'm tracking this building for a year. I'm tracking all this stuff. I talked about that, where that little tab was missing that cost a lot of effort on the part of the everybody. Cement substitutes, hard to predict and hard to hold the line. Pre-planned schedule, the cement replacement landscape is shifting. For example, ground glass is a new thing. Eagle eye on submittals. This building was what they call fast track, because the school wanted it by a certain date and didn't give enough time for full design. So the architect said, I'm happy to do this, but here's what happens. Stuff like that, here, what you're looking at was not sufficiently detailed. And so a lot of head scratching on site. This building has 40-foot trusses. The uplift, we figured, could be as much as 3/4 of an inch or an inch. Plus there's some deflection that the structural guy wanted to include in there. So the trusses are set above the partition walls. I forget exactly what, 3/8 gap. That was to allow for deflection. What that allowed us to do, in the middle picture you can see, you could take the roll of Intello and just feed it over the top of all of the partitions, tape it all together. We had this wonderful, complete Intello air vapor, variable vapor retarder. In this picture here, you can see these cool fasteners that the CM showed me. The structural guy had clips, you know, with slots and stuff. These things, you just screw them up through the top plate up into the truss, and the only place it has threads is in the truss, so that you can absorb that motion while still retaining the lateral movement of the thing. So yes, it makes a bunch of little holes, but they're filled with the screw. I'm not worried. So that's some of the things we learned along the way that are the kind of problems. I'm sure I'm not the only one that's ever run into them.
All right, I'm gonna grab that from you. So, having seen all that, as Andy mentioned, we had a client that had really good goals in place around trying to reduce total carbon. So a big focus for this case study on us was how do we analyze both for the operational and the embodied emissions and create a good structure for hitting the client's goals throughout this entire design process. So again, bring us back to this first graph. If we're looking at sort of cumulative emissions under the curve of the operational emissions, that's what we're showing here. I have been seeing increasing amounts of sort of research and literature out there.
Let me say something here.
Sure.
notice this isn't that graph of what's staying in the atmosphere. This is a graph of what's put into it. So
And
that's why they
pulse.
look so different.
Exactly. I see a lot of analysis looking for a payoff point or a balance point or say like a trade-off between embodied and operational. And if you sort of map the upfront emissions at roughly 25 tons, we see in about a decade there's a crossover point. And for our purposes of trying to create low-load buildings, that's not useful. Like, that's not a point that helps us lead towards answering important questions to achieve a better goal. There are some applications in which that can be meaningful if the constraints around your designs is more limited and we have to make some sort of a trade-off scenario. At that point, you've already lost a whole lot of control over the project, and that's not a good basis for trying to understand how to combine these two. It's also not what the atmosphere experiences. This is not an actual, like, good analysis of what the emission profiles of our buildings look like. So I would just encourage, if you're seeing these like trade-off or balance point analyses, it's really important to understand what is the question that is trying to answer. And if the question is around how do we reduce the total emission impacts of our buildings, I would suggest that's not the most useful place to start. This is what's actually happening, and the goal is to reduce both the operational and the embodied. And this is confusing enough that to be able to just simplify, we need to try to manage for both things and keep our focus around total emission reduction. What we're about to walk through is all of the opportunities there are to do that, where it does not have to be a trade-off between two things. If you find yourselves in a position of needing to make a decision between those two attributes, again, we're already probably really far along down the path and have boxed ourselves into a corner in which we have fewer good decisions. We have the opportunity to look at this early. We can optimize for reducing across the life cycle, both the embodied and the operational. And yep, want to jump in?
This is not the building we've been looking at, right?
Correct.
Okay.
This is a different building.
Clarify that.
Yes.
This is
From another modeled source.
Okay.
Yeah. So just to break that apart a little bit in terms of where there are so many opportunities to reduce both operational and embodied emissions within some of the same strategies. Andy was very clear about identifying what a burden it is to have these really complex building forms, multiple different roofs, 22 different corners. Simplifying our buildings, we know this so well from the operational side. You're reducing the surface area, you're reducing the likelihood for thermal bridging and leakage and everything that comes with these complex building forms. We're also reducing the material intensivity it takes to actually build these structures, the amount of waste that comes from all of these corners and these weird shaped assemblies. So we're immediately reducing our embodied carbons associated with the materials at the same time we're reducing the operational emissions by simplifying our form. And we're also reducing costs significantly. Again, coming as a builder, we would maybe name prices on a cost per square foot. When we're doing our estimating, the estimating is based on cost of lineal edge of transition. That's where the costs really show up in both design and construction. So if you have a strategy that reduces embodied emissions, operational emissions, and cost, yes, do that. That is gold. And architects in the room, thank you for all of your efforts to make simple forms look beautiful, because that is the value you bring into this environment as well, so that these strategies are actually useful. Insulation gets a lot of attention, and we'll talk a little bit more about that, but as we saw, there is an increased amount of emissions that can come when you go from a code minimum building to a higher performance building because of the increased consumption of insulation. As we saw from the total modeling, we would never suggest that you disregard the operational emissions. And the code minimum, that's what was driving those emissions. I would say there's no compromise in needing to create high performance buildings, but I would say it's a false narrative to expect that therefore you have to expect an increase in embodied emissions from your insulation. No, you pick an insulation with lower embodied emissions wherever you can, wherever it serves all the other functional purposes in the building. And if you have the opportunity, you can get to a carbon storing material that can serve well as an insulation and actually be benefiting on both sides of the ledger, the operational and the embodied. We can kind of go down the line, but really any time there's a core strategy around reducing the operational emissions, at a minimum, we can significantly mitigate the embodied impacts, and in some cases actually solve for both problems at the same time. And that's what I would recommend as our basis for trying to understand what are like not just the theory, but the actionable strategies in reducing total carbon emissions. I want to hone in on the mechanicals for a bit because that's another really great example. I've been now in 3 years deep into study around the embodied carbon emissions of mechanical, electrical, and plumbing equipment. And we find some really interesting pieces here. So what we saw is there's a big transition towards electrification, not just around reducing the total energy, but also the emissions that come from the use of that energy. And we move from fuel oil or propane or natural gas into renewably powered electrical systems. That's a win. That's the value of switching over to heat pumps. We also saw that refrigerant leakage was a big issue, right? That was a really significant plume. And across the MEP category, that tends to be one of the largest drivers. So the answer is to not, don't put in heat pumps. The answer is to manage refrigerant effectively as well. And when we look at some of the issues that come with the transition to heat pumps and the oversizing of heat pumps that has been sort of kind of an endemic challenge in making this transition, we see the operational penalties of that. It's using a lot more energy in a short cycling environment. It may depreciate the system life, and there needs to be more system replacement over time. We can see it can create, I live up in Vermont, we're starting to see lots of dehumidification issues from oversized systems on the cooling side that now require dehumidification and more energy use over there. So when we right size our systems, we have this whole checklist of wins, both in the cost and the operational side. It also has all these wins on the embodied side. We're using less equipment, there's less metal and circuitry that's going in there. We have less refrigerant charge to leak when our system designs are simpler. We don't have 6 different heat pump heads in every single room in the building. We can actually make our systems a little more compact. We go for ducted distribution or hydronic distribution. Now the likelihood of leakage goes down as well. We just see value upon value upon value as we follow a path of load reduction that is also benefiting the embodied carbon side. And when we can find those types of strategies, those are the ones to lean into and reveal all that additional value in case there's still any question as to whether or not load reduction is worthwhile. Now we just have more reason to say, yes, it is. And if we can follow the strategies that solve for both of those problems. And this curve should look really familiar. Anyone who's been in cost estimating knows that if you get in earlier, you have more opportunities to reduce costs. The x-axis is where you are in the design process. The y-axis is the potential of improvement. We've definitely seen this, and everyone that's been involved with high-performance building knows it's a lot easier to successfully achieve a high-performance building when you're in schematic design as opposed to when you get called into the beginning of CDs to make it a passive house at that point. It's the exact same scenario with embodied carbon reduction. Those of you that are in the adaptive reuse and building restoration space, you are heroes from an embodied carbon standpoint because the lowest embodied carbon building is the one that already exists. Those materials are already there. The emissions are already in the atmosphere. We can extend the service life of that building. That is the #1 win. And then moving on from there, again, building less, building more simply, being just a little more clever and intentional around how we manage the materiality of our buildings often saves money because if you're reducing the amount of material emissions and the quantity of emissions, remember, it's the quantity times the emission factor. If we get the quantity down, you're also saving money. So looking for these early design opportunities can really help us land into those blended strategies very effectively and cost effectively. I want to talk about carbon storage. This is maybe the most confusing / controversial topic around this entire issue of carbon. So I'm going to start by a really quick high-level look at global carbon cycles. And it's important to enter into this for recognizing that carbon dioxide is moving, and carbon actually as an element, is moving into and out of 7 different pools of storage on our planet at various rates in various directions over different timescales. And this is a very complex system we're entering into. Our way of thinking about this is typically just looking at the left-hand side of this graph, where we're looking at plant carbon that over millennia has been concentrated in deep pools of storage below the surface of the Earth. And we, as humans, are accelerating, we're participating in an acceleration of the carbon cycle of extracting that carbon from deep out of the ground, burning it to create energy, and aerosolizing that carbon dioxide into the atmosphere. And we know that's having a negative impact on temperature stability and climate stability building and the planet, and we need to do less of that. And so the reduce harm is the left-hand side of, that's what's behind load reduction and electrification, burning less petroleum, so on and so forth. That is critical, fundamental, necessary, absolutely important, and wholly insufficient. Because zero is not a sufficient goal when we're already past tipping points of planetary balance. So when we talk about like concepts around carbon capture and storage and some of these technological solutions, the most effective, cost-effective, and scalable carbon capture storage solution on the planet are plants. And so in the same way that we're participating in an unhealthy way in accelerating the carbon cycle from petroleum reserves up into the atmosphere through energy exploration, we can also accelerate the decarbonization of the atmosphere by recognizing, safeguarding, and supporting photosynthesis through plants. And that's where, as those of us working in the material space, have a ton of opportunity to intervene and support that part of the carbon cycle. I'm also going to call it oceans are roughly 78% of carbon pool on the planet. So any of the actions that we're doing that are depleting the biodiversity and ecosystem health of oceans is arguably having every bit as much of an effect on the atmosphere as our direct emissions from burning stuff. So if we really want to get global carbon cycle about this, we can talk about oceanic biodiversity health. That's maybe a step beyond what we're going to talk about today, but just highlighting some of the complexity and just trying to bring our scope of analysis from just doing less harm in one part of the cycle and recognizing how we can actually positively and proactively engage. It's not just theory. This is one of a whole series of studies. This is maybe one of the larger studies that came out of the UN a number of years ago. One, identifying that that materials and material emissions are one of the largest categories we need to address to hit our 2050 reduction targets. And then two, recognizing that bio-based materials and carbon storing materials are one of the fastest and most effective ways of being able to achieve some of those reductions. I recommend that and other adjacent studies that give a databasis to this. There's also a really strong market basis to this. So Amazon, as amongst many other tech companies, have been funding a significant amount of research into supply chain management and forest ecosystem health and forest ecological carbon flows, and really trying to understand and map this out, because they have a very significant market valuation for understanding this. So it's not just academia, there is also a huge market push around trying to understand and figure out how to calculate and do this well. I'm not advocating for any one position or the other, just identifying some of the basis of this research. It's not just our theory. Buildings for Climate Actions, the company I work with behind the BEAM tool, we found to try to be able to apply good strategy, it's actually really important to disaggregate the different types of bio-based and carbon storing materials to understand what the relative risk and uncertainty is around them. And we've broken this into essentially long and short cycle categories, meaning time cycle, the amount of time we expect it's going to take for that plant to grow, its growth cycle, or how close that carbon is to its end of life cycle. So we talked about using cellulose. The vast majority of the paper products going into cellulose insulation are coming out of the recycled waste stream. There's not a counterfactual scenario where that's just going to likely, stay in physical form. Some of it may within a landfill, some of that's going to turn to methane, a lot of that's going to turn to carbon dioxide. So we're diverting waste stream materials to increase its residency as a physical material in the built environment for decades to come. Ag and forest residues, those would be materials that are created from grain production or from forestry production that otherwise would go through its end of life cycle and decompose and burn and get back into the atmosphere. We're intervening with that cycle to use that as the feedstock for a novel material that gets stored in the building for a long period of time. Purpose-grown crops, lab-grown crops wouldn't otherwise have photosynthesized. They wouldn't exist were they not planted for the sake of creating a feedstock for a material. Those are all
Like straw.
Straw, well, straw I would consider a residue material. So if we're growing grain, we've got billions of tons of straw that's otherwise going to end up back in the atmosphere, a little bit in the soil, a lot of it back in the atmosphere based on North American ag practices. We feel good about giving a carbon storage value for that. Wood products get a little more complicated because they're a very long life cycle and it comes from a very complex ecosystem. And as John was talking about on Monday, it's a little hard to identify whether the atmosphere benefits from that tree being cut and put into a building. In some scenarios, yes. In other scenarios, no. It's a little more complicated. For those of you that are visual learners, I'm going to kind of repeat this with just some more diagrammatic information. So this is looking at straw. I've been building with straw in the Northeast for 25 years. I've been testing moisture within those walls for 25 years. I feel very confident about its use as a building material under appropriate design conditions. We can talk about that over beer later. But using this as a reference case, there's a ton, or many tons of carbon dioxide going into that plant on its annual growth cycle. It goes through its growth cycle. The very tops of the plants get cut off for food, and the rest of that straw typically is either burned or anaerobically decomposed into methane, and some of it gets filled into the soil, but really most of it's ending up back in the atmosphere. Some of it goes into bedding or landscaping, but goes through a very short cycle before it's going back up through its decompositional phase. The thesis here is that we interrupt that cycle and bank it as a long-lived building material and keep it out of the atmosphere for a longer period of time. That's the goal, is take a waste product from one industry and appropriate as a feedstock for a new industry while displacing higher emitting materials that would otherwise be used for that installation. So we're reducing the impact by displacing more industrially intensive materials while also banking carbon and keeping that carbon out of its cycle going back into the atmosphere. It gets more complicated with wood. We're talking about a 30 to 60 year harvest cycle for wood. So right off the bat, when do you start the clock? When that tree was cut or when that tree is replanted? So there's already some confusion around a longer period of time as to how you value when that carbon was stored or emitted. There's also the lost capacity of that tree. Would that tree have continued to photosynthesize for decades longer, or will it have been killed in a fire or killed by beetles, or needed to be harvested anyways as part of another management criteria? Because of the complex nature of these forest ecosystems, there's a tremendous amount, usually depending on the forest, anywhere from 1 to 3 times the amount of carbon in the aerial parts is actually in the soil. So soil disruption from forestry practices is another complexity that's not always captured within this analysis, so on and so forth. There's other, roughly only half the tree may end up making it into a building. The rest is slash, usually left to decompose. I'm not saying that wood is good or bad. I actually think wood is a critical solution as part of our building palette. It's just more complicated to do quantified analysis around the carbon flow impacts with wood because they're from more complex places, complex ecosystems, and have longer lifespans.
Can I say something? So when I first started looking at this stuff, I thought, well, okay, if we have FSC certified sustainably harvested wood, we could count that as carbon storage. Well, and we count cellulose. Well, does that mean we should now make 3-foot thick walls of cellulose? Where we're storing more carbon, right? This is all good. No, it's about total consumption.
Yes.
So this storage and how you count that is complicated, and we erred on the side of conservative in the analysis I showed you. We didn't count the wood.
We didn't count the wood
as storing carbon.
Right. And the rule of thumb I would generally say around do you count the wood or not is if you know the provenance of the wood product, you know the forest management practices of that wood product, and you can convince yourself that the atmosphere hasn't been harmed from deforestation practices based on that harvest, give it credit. If you can't confirm that, be conservative. Don't give it that credit unless you really understand the chain of custody of your wood and the point of origin from which that wood came. Okay, so here's a whole other argument we hear very regularly around sort of discounting the legitimacy of providing a negative emission value for stored carbon, for sort of valuing carbon storage, which is it's not fair to count a negative emission during the product lifespan and disregard what happens at the end of the building's life and understand that, well, the assumed scenario, actually by international regulation for life cycle assessment in buildings, we have to assume that all of that carbon goes back up into the atmosphere at the end of the building's life. To which I would say, fine, that's very legitimate to look at the full life cycle and recognize this is part of a cycle. We're not permanently entombing anything in these buildings. We just saw a whole thing on fire, so we have good understanding that our buildings do not live forever. That is very legitimate. But the problem with that sort of static accounting is that it doesn't give any valuation to the intervening 60, 80, 100 years of time between that release, or that storage and that release. And we need to look at that also. Both of those things matter. So my argument is that we need more than one type of analysis to understand this stuff. So let me break this down a little bit more. So this should look familiar. Now we're looking at the time quotient in our analysis. This is a very similar shaped graph to what Andy showed in the case study, how we mapped this out. In this case, just to explain what we're looking at, this is not the same building. This is modeling, came out of the University of Bath, where you look at a 1-ton pulse of emission that happens on year 0. and the y-axis here is actually, it's not carbon dioxide, it's the global temperature change. It's the radiative forcing, if you want to be technical about it, that occurs as a result of that emission being released. And so there's sort of a similar shape, right? There's a decay curve in the atmosphere, and we can see that there's, as the emission is in the atmosphere over this period of time, there's a temperature increase associated with that, and then that tapers down as the decay curve of carbon dioxide follows. You're seeing another pulse at year 60 reflecting the end-of-life emissions of that building, and there's another pulse at the end of its life, and then again, a tail that follows. This is what essentially we were showing with the cumulative analysis that Andy showed with all those beautiful stripy graphs.
And so that bump at year 60 is what, the excavator crunching the building?
Yes, exactly. And the sort of decomposition of all those materials and the processing energy, all that jazz. That's what would be in that phase of life. So similarly, when we look at the value of having actively removed a ton of carbon dioxide out of the atmosphere, this isn't theoretical and it's not way back in history. This is photosynthetic decarbonization of the atmosphere, and then the carbon that has then been stored in physical states, the impact of that being out of the atmosphere a 60-year period of time, and you look at the area, in this case above the curve, is quite significant, such that even if we assume a total release of all of that carbon dioxide after 60 years, it just makes a relatively small, here we go, this little dark overlap here, that is the net warming effect over that same period of time for having avoided that ton of emissions for 60 years.
Anyway, so this blue one down here, let's say you've got enough cellulose insulation that you stored a ton.
Yeah.
And then you're saying at the end of 60 years, it goes into the landfill and...
Let's say 100% of that carbon is back up into the atmosphere. This is the net warming effect over that same 100-year period of time. So that time factor is really relevant. Like, time actually does matter in this equation for a couple of reasons. One, we very much need this temporary cooling effect now. We need to buy ourselves whatever time we have to be able to improve our practices, not just in construction, but in end-of-life waste management and decarbonizing the more industrially intensive parts of our economy. So we need that. It's also, I would argue, really poor analysis to be trying to make reduction goals in the next 15 to 25 years, but using a 60-year time frame of total carbon flows. That's the wrong time boundary. If we want to look at what are the end-of-life impacts and look at reduction goals at end-of-life of the building, absolutely, assume all those emissions are released. But if we're trying to make reduction goals between 2030, 2040, 2050, the end-of-life doesn't matter by that point. I'm not saying it doesn't matter at all. It's just the wrong time boundary for the analysis. We need a form of analysis that allows us to look at time and understand what the net impact is within those shorter time scales to hit our near reduction goals. So the last thing I would say is, in terms of buying that time, if we just were able to capture 20% of the carbon coming out of our buildings, so let's say that cellulose, if we could recover 20% of that, we would have no net impact on emission release at end of life. So we could actually really use that time to be able to improve our end of life management practices. This is where carbon storage starts to connect with principles of circularity that we could use time to figure out. Mark, you had a question there.
Does the blue portion, is it different for wood framing where someone cut a tree versus cellulose?
The question is it different for wood studs than for cellulose? I would say bigger, well, the favorite answer of any
It depends.
It depends. If that wood is beetle kill pine or a wood, it depends on your wood scenario. If you're talking about a tree that otherwise would continue to happily photosynthesize for decades into the future, I'd say yes, that is different, but that's not what's shown here. This is just looking at the impact of a ton of stored carbon independent of its provenance. That's why we break short and long cycle into different categories to help answer some of those larger system boundary questions. So I want to just try to reconcile these two accounting methods because there's been a lot of confusion around this. The way to think about this is, if we're trying to count carbon and really trying to do the accounting of the carbon, yes, that +1, -1 methodology of, you subtract you store a ton of carbon here and then you release the carbon there, totally appropriate, totally valuable. If we're trying to understand what is the value of that carbon, what is its actual impact in the atmosphere, we need time as a factor to have a good understanding of what those impacts are. And it's not unlike money. When you're trying to figure out like your ledger of accounting, yeah, you want to know what the pluses and minuses are of your account, but that's not going to tell you, oops, advancing quickly, that's not going to tell you the impact of interest, right? That's not going to give you the time value of money or the opportunity loss or costs of having invested or not invested. We need to look at it from both of those perspectives. I think about this, prior to embodied carbon, a huge focus of mine was as an energy analyst working under Andy, and I'm not using my peak demand, my peak energy loads to size my solar system, and I'm not using my annual energy to size my heating system. We need to look at the same thing from two different perspectives to come up with a comprehensive analysis, and that's the argument here. One is not better or worse, so you make sure you're using the right analysis to answer the right question. So if you're trying to answer how does carbon move within the system, yes, that static LCA +1, -1 is appropriate to look at. But if we're actually trying to understand how does the climate respond to these carbon flows, we need the value of time. We need to look at this in more than one way to get a complete picture. Okay, I'm going to wrap us up here, and then we can chat. So
Take a deep breath.
So we know we want to try to get towards carbon storing buildings. That would be our hypothesis, to get to true net zero, because we're still going to be pouring concrete and making glass and producing these industrial products. So if we're trying to get to a true zero carbon building, there needs to be a counterbalance to that. We had started from a place of just basic literacy on this within the last X number of years. So we're finally now at the point where we've got research and we've got data, we've got tools, and we've got some burgeoning standards and best practices. We're now, right now, on the verge of having a standard in North America, ResNet Standard 1550, that will help give a consistent methodology for how we do this accounting and apply this in practice, which is going to be a critical step in terms of being able to do this uniformly and develop incentive and regulatory structures built upon a consistent consensus-based standard. So, just to kind of highlight that trajectory of our industry right now, Builders for Climate Action has now modeled hundreds and hundreds and hundreds of buildings over the course of a series of different studies, and have found some very consistent patterns for low-rise residential construction. This is single-family, multifamily, townhouse, low-rise residential. And we find concrete is still a really big deal in those buildings, and in part because the framing is so low. Anyone that's looked at this, and John talked about this a bit on Monday, big, heavy buildings that are more structurally intensive have a larger plume of emissions from the superstructure, but in light frame, wood frame buildings, like that's pretty minimal. There's not a whole lot of emission there. So we see the concrete jumping out. These are also the same way from an energy perspective, these are skin-dominated buildings in their loads. They're also skin-dominated buildings in their material consumption. So we see insulation and cladding jumping out a lot. John started querying, well, why does insulation get so much attention? Well, because we found over like 700 buildings, it's pretty consistently the second highest cause of emissions. And so, great, that's just good to know so we can pay attention to managing for that. Again, let me be super clear. We are not suggesting that you have less insulation in your building to save on the embodied carbon. No, we're suggesting you get a net zero high performance building and also use lower carbon materials to achieve those goals. And then cladding is another huge one. Interiors start to become a really big deal as well. So this is what helps point us towards prescriptive approaches, that we shouldn't all have to be modeling every single building. That is impractical and unnecessary and a waste of resources. But now we can start seeing enough patterns where we can start pointing towards some prescriptive approaches and at least narrowing our fields of where we need to pay attention, because there's already too much to pay attention to. All right, so wrapping this up here to talk about this 1550 index. So a lot of credit to ResNet, starting the HERS index looking at energy. They have already over the intervening years recognized that that there's more opportunity and more imperative to look at not just the energy profile of a building. The HERS hot water index allows us to look at hot water usage and intensity, and the HERS carbon index does that thing that we've been talking about. It's not just the energy, but it's the emission factors and what's the actual operational carbon emissions. The carbon index does that with a push of a button based on some of the same predictive data that Andy showed in our model. And then the next step of that is the embodied carbon associated with the production of the building. And what's incredibly exciting about working within this ResNet program is that it's the same folks that are assessing buildings for energy are also assessing for embodied carbon, which gives an opportunity to develop strategies based on the same workflow and not have those two workflows being siloed and isolated. And so this is already well underway. There's some wonderful ResNet folks in the room. Mike Brown's here. Are anyone else involved in this project? Raise your hand. Oh, go find Mike. There's a Northeast HERS Alliance. Not only was involved in getting 1550 into motion, also involved in this 100-home benchmarking study. The report will be out within the next couple of months. Not only do we now have a benchmark assessment of typical embodied carbon levels of 100 homes within Massachusetts, we were also able to work through rater workflow issues and understand the friction points around conducting these assessments. We're able to give the standard a pilot run to be able to improve the quality and performance of the standard. As a tool provider, a software person, we were able to work with an energy rating software provider and understand how do we actually get the software to work as effectively and efficiently as possible to reduce the burden off the rater of having to do multiple endpoints and try to square analysis between two different tools. So we're already that far along the way, which means that as I would ask you all to keep your eyes out, the final public comment review for 1550 will be hitting the airwaves in the next month or so. We warmly encourage you to provide your, I would argue, support or your feedback around that standard, because this is the trajectory that this work is following. So to wrap us up, it's very useful as we get completely caught in the weeds and all of the parsing of the numbers and the data and the framing of the structure for me to remind myself of what the value of conducting this work is in the first place. It is so easy to get lost in the building as the only boundary condition that we reference in making decisions. And the real challenge that we have as practitioners is to understand the broader impacts of this. And if going from an energy modeler to an embodied carbon modeler, that was the big challenge. I had to expand my temporal and spatial awareness and boundary analysis to be looking upstream and to be looking downstream, because that is both the impacts that we have in the development of built infrastructure, and that is also the influences that are impacting our buildings as we continue to move forward into a century of climate destabilization. And so having some grounding reference of the value of why we're doing this work in the first place, I'd like to be able to include some of that imagery and also the metaphor of the fact that this is a highly emergent and very nonlinear path towards how we improve the development of our buildings. It's very simple, especially right now, given some of the tumult in our political and economic environment, to feel like we are literally going backwards. And it is very useful for me to recognize we have a North Star. There is a vision and a direction around a healthy, safe, and low carbon society that we can continue to orient ourselves towards, even as the river takes its bends. Those of you in the permacultural space knows that we just have more edge connection. There's just more opportunity as our edge increases, but we can keep our direction pointed towards our North Star.
Don't change it.
Oh, don't change it.
I want to connect a couple things I heard yesterday. Mark was talking about daylit buildings, which are one of my favorites. It's, daylighting is one of those few things when you walk into a building, you notice. We do a great job on the enclosure and the mechanicals, and our job is to make sure nobody notices. But this is something you notice. And then folks were talking about remediating these horrible buildings and the horrible impacts they have on people. And it made me think about the building I worked on, the energy systems building in Vermont that Bill McClay was the architect for. Again, a great client. He said, I want the best building possible. Give it to me. And he had the budget and the will to do it. This building has great indoor air quality. It has beautiful daylighting. They were so proud of this building, they made a video about it. And in this video, there's an open office area with this beautiful daylighting in it, separated from the corridor with this, planter on top of a little partition wall. And the woman who tends the plants in the building, she's on this video, and she says, I don't know what it is, but everywhere else, I have to replace plants every 3 months here. So here they just grow. Then there's another woman who's in the video who works there. And she says, in the old building, which was an old Butler building that they were in, I was out probably a week or two every 2 months with allergies. She said, I haven't been one day out since I've been in this building. And this, for me, gets to this notion of reciprocity. We've been trying to do better and do less bad. We need to get to the point where what we're doing is nurturing. These buildings can nurture the people in them. The way we build them can nurture the environment. It's, Robin Wall Kimmerer talks about it as reciprocity. It's not we have to stop doing the bad stuff. We have to start giving back. And some of this bio-based these bio-based materials, they're an entry point to that. And I want to tell you one little story. So my wife was friends with Orrin Lyons, who's the story keeper for the Onondaga Band of the Iroquois. Cool guy, he's in his 90s by now. So she goes and visits one time with her girlfriend, and he's got these cool artifacts in there, and he's got this megaphone sitting on the shelf. Carolyn says, "What's that?" "Oh, it's a moose call. You want to hear? And you want me to show you about this thing?" "Oh, yeah," she says. So she and her girlfriend's so excited, they go outside. Orrin picks up this megaphone, puts it to his mouth, and he says, "Here, moosey, moosey, moosey." So my daughter was about 10, and she heard this story. She says, "I want to go visit this guy." So Carolyn and I look at each other, we call up Orrin, and he says, "Oh yeah, come on over." He meets us at a diner somewhere. And Orrin says, "You know, all our prophecies say it's all going to hell in a handbasket. They're all very clear about this. But they also say you can't let it happen on your watch." And for me, what I've taken from that is I need to do what I can. I thought I was going to retire by now, and it doesn't look like I can. And it releases me from feeling like what I'm doing is not enough. We do what we can, and we make that impact. We try and look for this circularity. We try and move from this place of do less harm to reciprocity with the natural world and with the people we impact with their building. So I'm very appreciative of all of you and your attention today and for this wonderful gathering. Thank you all.
Whoa. We have time for some questions.
I just want to point people to that beam tool that they talked about at the very beginning. I've been a beta tester through the first 2 rounds. Thank you very much. And what I've learned is I have really strong intuition about energy and strategies and approaches. And my intuition about carbon and low carbon is 0. So you have to learn this thing all over again with math, and it's about assemblies, not materials. So I really think spend a half a day with the beam tool on a project, and you will learn so much. And both of you, thank you so much. Oh, yeah, you absolutely have to pay them some money. I mean, Jacob and Chris and all these people have been doing this work, as well as the beta testers, unfunded research.
I am happy to say, this before the next comment, I'm actively redeveloping the beam tool as we speak. So for those of you who have used it and have been a little frustrated with some of its liabilities as a spreadsheet tool, it'll be re-released within the not too distant future as a much more facile and easy to use tool. So good things to look forward to.
There's also places if you want to get involved in this whole thing. I don't think you mentioned Carbon Leadership Forum.
Oh no, there's...
So this is a bunch of folks trying, tell me if I get this right, bunch of folks trying to get this stuff into the mainstream, like get the fire testing, get this, whatever kind of testing's needed so that this stuff can go from like niche residential to, you know, wider adoption. Is that fair?
I would actually say that the commercial sector is leading on the embodied carbon work, and it's the residential sector that's really now starting to come of age and realize we have a tremendous number of advantages within our building types. But yes, Carbon Leadership Forum is a great organization for bringing that community and that research base together.
I thought it's a great presentation, very important. As a scientist, I'm often asked questions about embodied carbon and stuff. And for me, what helps put it in perspective is a couple principles. First of all, 1/10 of 1% of our atmosphere is what's responsible for the warming. And so when John Straub on Monday said that during his lifetime, that level has, CO2 has gone up 100 ppm, that's like 10% of what is contributing to radiative forcing. And the other thing that's kind of scares me is that the amount of CO2 that we have today, we will not see the impacts of that for decades, because these processes take time to work their way through. So it really is impingent upon us to do these kinds of efforts, because it's going to be, it's serious business. So thank you.
Yeah, I'll say thank you. Also, thank you again to both of you. I'm struck by and I think these are statements, but I'm interested in your feedback. You said over and over again, it's about analysis boundaries in terms of time and space. The economic time frame is shifting dramatically, and I think anyone here who's thinking, okay, what does this cost? What's the cost benefit, et cetera, according to the typical rules, needs to recognize just in a group of housing lawyers, basically real estate lawyers. And they were saying, well, yeah, we can't get it built. Don't add anything else. Don't concern me with this. However, the time frame is shifting dramatically because extreme weather is having impacts on insurability. And yet, as was just said, the carbon release has these long-term impacts. Insurability could be tomorrow. Like, how do we even connect these different timeframes? So if you can't insure property, you can't get a loan, the financial system collapses. There is no more ROI calculation that can address that. That's one point. So how do we connect those? And the second one is that there are lots of other planetary boundaries, and you're talking about carbon today, but there are 8 other planetary boundaries that have been quantified. Several of them are in overshoot. I have to believe there's synergistic relationships or multiplier benefits, and we heard so much about health. So when we debate the embodied carbon of foam versus straw, just to take 2, we also have to ask, if there are 25,000 industrial chemicals going into these products and only a couple hundred of them are regulated, what's the chemical exposure of these cocktails? And we can also address the bio-based benefits in that domain as well. So that's all I'll say. Thank you.
Thank you, Dash. I want to have a really quick follow-up on that. It is a great risk in this research to fall into the trap of having carbon blinders on. And as a carbon researcher, I will be the first to acknowledge, like, that is a dangerous trap. It's not the only metric. In many cases, it's maybe not even the best metric, but it is also a critical metric. I want to bring back that picture in your mind of the global carbon cycle. If we're really, really trying to serve goals of atmospheric chemical stability, to reference the scientist's prior comment there, we should be caring every bit as much about the amount of microplastic proliferation into the oceans that are depreciating oceanic biodiversity and the ability of oceans to actually absorb carbon dioxide out of the atmosphere, because there's way more activity happening there at scale than there is from our direct emissions. And so, yes, looking at multiple attributes, it's hard and complicated, but we're learning more about it, and there's more patterns that we can follow to help us synthesize that into actionable decisions.
At the same time, we don't want to be debilitated by only looking at the big picture, which can be so debilitating.
It's true.
We want to pick a place where we can work.
Exactly.
And we can have an impact, and we can do something. And that's, like Oren Lyon said, that's important.
That's what we can do.
I want to thank you for inspiring us to not give up on this mission, even as dismal as it might look. Sometimes it's easy to just, I don't know, kind of just keep looking down and keep going. So thanks for that. I may have missed this, and pardon me if I did, but I was wondering if you could speak on any feedback you have on site generation of energy, PV panels, and battery storage, and the carbon impacts of that. And we're all looking at net zero buildings, so seems like that's a really big piece.
You want to start?
Yeah, PV and batteries, all good. I think this, this electrification revolution that's going to happen if we're going to stay on this planet in some reasonable, recognizable form, it's going to be herky-jerky. Oh, we want electric cars. Let's get a bunch of, now we need some chargers. Oh, now the grid isn't supporting it. Oh, now, so it's my feeling is we need to press where we can, where we've got an avenue we can put this wedge in to the system and do that. And PV and batteries are a great one. Yes, it's full of toxic chemicals in these things, and a whole bunch of stuff around that. But we can reuse those. They last a long time. Recent studies show on cars they're going to last twice as long as we thought they would. And at the end of that stuff's all still in there, and we can reuse it. So I'm not too worried about the impacts of those. I tend not to look at payback. When somebody mentioned ROI, the inverse of payback, my experience is when I tell someone the payback, it's never enough. And it's like, I don't care if it's 2 years or 10 years, it's never enough. And there's no payback on destruction of this beautiful planet. How do you do that? So yes.
The two little comments I'd add is from the times we have actually looked at the embodied emissions from photovoltaic infrastructure relative to the benefits of renewable energy generation. If you do need to name it in terms of payback, it is well within the lifespan of that equipment. So that's useful. And just another big plug for load reduction, because we just need less of that if we're smarter about reducing our loads. And again, win, 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 less cost, less infrastructure, less embodied, less all the things.
All right, last question before we eat. These people are going to be available to answer questions all day.
All afternoon.
Thanks for the talk. Love it. I think we have a very significant parallel effort going on at FIAS. So I think there's an opportunity to collaborate there if we can get together on that. And my question is about the future analysis. So you've taken an energy model and you've applied these Cambium projected rates, but were you using future projected climate data as well for that? Are you rerunning a TMY3 through the different projected grid emissions?
That's a good question. My energy model is running TMY2 data that's 30-year averages that are now 20 years old.
Yeah.
And there's folks working on getting new, more up-to-date stuff. And I think one of the reasons this building that I'm monitoring is an EUI of 20 instead of 15 is we've just been through this hot summer, and it's an air-conditioned building. This building, by the way, is participating in something called flexible load management. The local electric utility, if they see a peak coming, they can adjust the thermostat up for a couple degrees and then turn off the heat for the 5-hour period or whatever. And I told them, don't bother on the heat side. This building, nobody will notice you turn down the heat for 24 hours. On the cooling side, yes, somebody will notice. But so it's a way to manage these things. We need to get smarter about the management, as well as just building things like batteries to do that management for us. There's ways we can do that without having to build a bunch of stuff.
I would like to suggest the remaining questions come and talk to these great speakers. We're going to have lunch, but first we want to say thank you, thank you, thank you.